refraction at spherical surfaces and by lenses. Consider a convex circular boundary of radius r and center of curvature c. The formation of image I of an object O on the principal axis of a spherical surface. The rays are incident from a medium of refractive index N1 to another of refractive index N2. We take the aperture or the lateral size of the surface to be small compared to other distances involved so that small angle approximation can be made. O is the point object, OP is equal to minus U is equal to object distance. P is pole, PC is equal to R is equal to radius of curvature. I is point image, PI is equal to V is equal to image distance. Angles I, R, alpha, beta, gamma are small enough for sin I, tan I to hold. N1 and N2 refractive indices of rarer and denser media with respect to vacuum or air. N21 is equal to sin I by sin R is equal to I by R is equal to N2 by N1. N1 sin I is equal to N2 sin R. N1I is equal to N2R. Equation 1. N1I is equal to N2R. Substituting I is equal to alpha plus gamma and R is equal to gamma minus beta, we get N1 alpha plus gamma is equal to N2 gamma minus beta. N1 alpha plus N2 beta is equal to N2 minus N1 gamma. Since all angles are small and Q is very close to P, MQ is equal to MP, we can write N1 tan alpha plus N2 tan beta is equal to N2 minus N1 tan gamma. N1 MP by OP plus N2 MP by PI is equal to N2 minus N1 MP by CP. N1 1 by minus U plus N2 1 by V is equal to N2 minus N1 1 by R. Equation 2. Equation 2 gives us a relation between object and image distances in terms of refractive index of the medium and the radius of curvature of the curved spherical surface. It holds for any curved spherical surface. Refraction by a lens. Figure shows the image formation by a double convex lens. The image formation can be seen in terms of two steps. The first refracting surface forms the image I1 of the object O. The image I1 acts as a virtual image for the second surface that forms the image at I. Applying equation 2 to the first interface ABC, we get N1 by OB plus N2 by BI1 is equal to n2 minus n1 by bc1. Equation 3. Applying equation 2 to the second interface ADC, we get minus n2 by di1 plus n1 by di is equal to n2 minus n1 by dc2. Equation 4. For thin lens, bi1 is equal to di1. Adding equations 3 and 4. n1 by OB plus n1 by di is equal to n2 minus n1. Suppose the object is at infinity, that is OB minus infinity, and di is equal to f, then the equation 5 become n1 upon f is equal to n1 minus n2, 1 upon bc1 plus 1 upon dc2, 1 by bc1 plus 1 by dc2. Equation 5. A lens has two foci, f and f prime, on either side of it. By the sign convention, bc1 is equal to plus r1, dc2 is equal to minus r2. So, equation 5 can be written as 1 by f is equal to n21 minus 1, 1 by r1 minus 1 by r2. Equation 6. Equation 6 is known as the lens maker's formula. Magnification M produced by a lens is defined as the ratio of the size of the image to that of the object. It is easily seen that for a lens, M is equal to V by U is equal to H prime by H. For erect and virtual image formed by a convex or concave lens, M is positive, while for an inverted and real image, M is negative. Power of a lens. Optical power or refractive power is the degree to which a lens converges or diverges light. It is equal to the reciprocal of the focal length of the device. P is equal to 1 by f. High optical power corresponds to short focal length. The power P of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light falling at unit distance from the optical center. Tan delta is equal to h by f if h is equal to 1. Tan delta is equal to 1 by f, or delta is equal to 1 by f for small values of delta. Therefore, P is equal to 1 by f. The SI unit for optical power is the inverse meter, m raised to power minus 1, which is commonly called the diopter. Converging lenses have positive optical power, while diverging lenses have negative power. Combination of thin lenses in contact. Consider two lenses A and B of focal length f1 and f2 placed in contact so as to have a common principal axis. The image formed by the first lens A, we get 1 by V1 minus 1 by U is equal to 1 by f1. Equation 1. For the image formed by the second lens B, we get 1 by V minus 1 by V1 is equal to 1 by F2. Equation 2. Adding equations 1 and 2, we get 1 by V minus 1 by U is equal to 1 by F1 plus 1 by F2. Equation 3. If the combination of lenses A and B is regarded as equivalent to a single lens of focal length f, 1 by V minus 1 by U is equal to 1 by f. Substituting in equation 3, we get 1 by f is equal to 1 by f1 plus 1 by f2. Combined focal length of two thin lenses in contact is given by f is equal to f1 f2 by f1 plus f2. If we have several thin lenses of focal length f1, f2, f3 in contact, the effective focal length of their combination is given by 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3 plus and so on. If P is the net power of the lens combination, we have P is equal to P1 plus P2 plus P3 and so on. Net power of the lens combination is an algebraic sum of individual powers.